So as we find our ways to our seats for the last session of the afternoon, so we have in Jakob Stein, recent member of the Unicamp family, telling us about gauge theory with symmetries and ALC G2 manifolds.
Thanks very much for, firstly to the organizers for putting on this great conference, and thank you for inviting me to speak. It's nice to be here for the first time. So today we're really going to be talking about two things, two kind of separate things, but what unites them is that they both give rise to a system of ODEs, time-dependent ODEs, which describe gauge theory on cohomogeneity 1 G2 manifolds. Okay? So firstly, generalization or an attempted generalization of what we'll call BPS monopoles to dimension 7. And a spoiler that it actually, if you want smooth and bounded, actually doesn't work. So that's a bit sad, but it has some interesting ideas there, and you get some explicit singular solutions. I thought it's interesting enough to talk about, but because it's a negative result and we want to cheer ourselves up, I'm also going to talk about instantons on a family called the B7 family of G2 metrics, and there we do get solutions. It's a two-parameter family of solutions for each member of the family, and what the interest for us will be how that two-parameter family varies as you vary in the family of metrics. And I should say that both of these are ongoing projects. The first was with Derek Harland at Leeds, and the second is with Matt Turner, who was until recently at Bath. Okay, so for those who don't know what a G2 or cohomogeneity 1 manifold is, we talked a lot, and there's been some talks that have mentioned G2 structures, but I just thought I'd give the definition so we know what we're working with. For me, a G2 manifold is going to be a 7-dimensional Riemannian manifold. G is my Riemannian metric. It's got a parallel 3-form, and the local model for what this 3-form looks like is going to be the following. So I think of my tangent space as the imaginary octonions. So 7-dimensional space, imaginary octonions, and then I take 3 imaginary octonions, I take the Euclidean inner product, and I form this object. I take the product with respect to the octonions, and then I take the inner product with respect to the Euclidean metric. Okay, and that gives you 3-form is a thing that you should prove for yourself. Okay, and then the other word is cohomogeneity 1. So manifold has cohomogeneity 1 symmetries, which means essentially that locally I can describe my manifold as a product of an interval, let's say 0 to 1, and a family of homogeneous spaces parameterized by t, which I'm using to parameterize this interval. And the metric on this space is going to split orthogonally as well. So I'll get this dt squared piece, and then the metric on the 1-parameter family of homogeneous spaces. Said another way, I have an action on my manifold of a Lie group that has generic orbits codimension 1. That's another way of saying this. Okay. And if you've never seen some examples, here's 2. So the Euclidean R7, my interval, I just take the unbounded infinite interval, 0 to infinity, and S6, where I'm writing S6 as the homogeneous space G2 mod SU3. And the metric I'm taking GT is now t squared times the round metric on S6. Okay, that's the Euclidean metric, written in this way. Maybe a less trivial example is the metric of Robert and Simon on S3 times R4, which is the infinite interval times S3 times S3, where we're viewing S3 times S3 as SU2 squared. And then I have some factors which multiply some explicit functions of t up to a reparameterization, multiplying the round metric on SU2 and SU2. And just when I write G plus, what I mean is I take the embedding, bigger. I've been told to write ridiculously large, so I take the embedding of SU2 into SU2 squared, either by the diagonal map or the anti-diagonal map. And I take the push forward of the round metric on SU2 via these two maps. Oops. Go back. So that's what that means. OK, but it's all explicit, and it's all sort of well-known things. OK, and these are useful for lots of sorts of problems because the slogan is that cohomogeneity 1 turns PDEs into ODEs, and ODEs, in principle, are easier to solve. So the problem that we're going to look at today, using cohomogeneity 1, is, oops, so that's going back, is the problem of monopoles and instantons. So what is that? I fix a principal bundle, P, on my manifold, and then I consider an equation for a pair, A and phi, where A is a connection on P, and phi is a section of the adjoint bundle. I take the curvature of my connection, I wedge it with the Hodge star of my 3 form, it's 4 form, wedge a 2 form, 6 form. I Hodge star it again, and I declare that to be equal to the covariant derivative of my phi. I sometimes will refer to, in this talk, phi as the Higgs field, but that just means that it satisfies this. It's this equation. And I want to distinguish two cases. One is when phi vanishes identically, and that's sort of the degenerate case, which I'm going to refer to as an instanton. And then when phi is not identically 0, I'm going to refer to that as a monopole. It should be noticed, if you haven't seen what this is modeling in 3 and 4 dimensions, so the monopole is modeling the 3-dimensional equation so the same idea. And the instanton equation, which is star phi fa. So this is 3D and 4D is minus fa. Instanton. And I'm going to refer to these 3 and 4-dimensional things as monopoles and instantons as well, just in case you get confused. OK, so I want to think of some examples that I can use these cohomogeneity 1 symmetries to generate me some monopoles and some instantons. OK? This is a thing that goes back to the foundation of the subject of G2 gauge theory, these one-parameter family of G2 invariant G2 instantons on R7 by Nikolai and Ganadin. So these model, perhaps the better known, SU2 invariant BPST instantons, I mean in R4, like those. And their construction is very similar.
What do you mean by SU2 invariant and G2 invariant?
I mean that there's an action, the action of G2 on R7 has a lift. I mean, there's any lift that you do that has a lift to the trivial bundle, for which the its action on the connection, its induced action on the connection, is trivial. Thanks for the question. So to me, a natural question is, given this, I mean, there's also a spin 7 story here, but I won't really go into that. But what about generalizing? There's SU2 invariant monopoles as well on R3. So could you play the same game? I mean, that seems like a very logical thing to ask for.
So what are the gauge groups?
So yes, good point. In each case, the symmetry group, so the G2 invariant, is the group G2. And in that case, SU2 invariant, the group is SU2. So for the monopoles, you have to do something a bit different. And I'm going to explain one way of viewing the BPS monopoles on R3, which will clarify what you should do. I'm going to think about SO3 bundle or SU2 bundle, if you prefer simply connected. And I'm going to write down a Higgs field and a connection which are invariant under the action of SO3 or SU2 on R3. Okay? So I'm going to use the identification of two forms on R3 with the Lie algebra of SO3. Okay? So given this identification, it's not too hard to cook up an invariant section of the adjoint bundle. I just take the volume form, so it's a 3 form. I take the interior product with the radial vector field. This gives me a 2 form on R3, and now I use this identification to declare this to be actually a section of the adjoint bundle, or a map from R3 into the Lie algebra of SO3. And then I will multiply it by some SO3 invariant function phi r. Okay? So to cook up a connection form, what I have to do is a bit more involved, but I'm going to pick a basis of, so EI, which is just dxj wedge dxk. These are the coordinate 1 forms, and ijk are cyclic permutations of 1, 2, and 3. So I pick a basis of my 2 forms on R3, and then I do the identity map from 2 forms to SO3. So that gives me a section. So remember, I'm identifying 2 forms. I'm identifying so 2 forms with elements in the Lie algebra of SO3. And then I take the interior product, so the identity map is this guy. Right. And then I take the interior product with the radial vector field. This gives me a 1 form with values in SO3, Lie algebra SO3. And then I multiply it by some some SO3 invariant function. Okay? And then imposing the monopole equation gives me an ODE for these 2 functions, and I can solve them. And it turns out they're in a 1-parameter family. Okay, nice. That's...
Same thing as the solution found by Polyakov.
So yeah, I mean, BPS, I guess it's the... it's a 3-dimensional... I don't know of the solution, but... to me, this is a classical thing. I actually don't know exactly what the history of it. Apologies. Right. So to me, the obvious generalization is, okay, I've taken my 3 form, taken the interior product with the radial vector field. In the G2 case, I've got another 3 form lying around, which is my 3 form, my G2 defining 3 form. So I can play the same game for the Higgs field. Right. And now the Lie algebra that I'm looking at is now SO7, or spin 7 if you like simply connected. Right, but now for the connection, I have to be a bit more careful because G2 splits the action of G2 splits SO7 into various components, and it's a fact that it splits it into a two-dimensional component, lambda 214, isomorphic to the algebra of G2, and then a seven-dimensional component, which is isomorphic to the standard representation of G2 on R7. Okay, so now I take the identity component, the identity map between the Lie algebra and the two representations of G2 as two forms, and then I do the same thing, take interior product with the radial vector field, multiply it by some functions, oppose the G2 monopole equations, I get an ODE. Okay, that seems like the natural generalization of what we just did for BPS. I hope that that's not controversial. And here they are. I've explicitly given you some equations. Great. Plus minus, I've just rewritten them slightly so they look a bit nicer. And you'll notice that if I set A7 to be 0, I actually get and I set phi to be 0, I actually get that, I actually recover the solutions, the instanton solutions of Nicolai and Ganadin. Okay, so we actually want monopole solutions. So what are these? And as if you know some things about G2 monopoles and you're scratching your head and thinking, it sounds a bit fishy that you would have monopoles, if you're thinking about monopole classes, if that means anything to you, why that might not hold is because there's no splitting into line bundles at infinity. The expected asymptotics of this guy would be sort of an analog of what's called non-maximal symmetry breaking, which is studied, for example, in the R3 case by Nagy and Charbonneau. And the connection that this should be asymptotic to would be the canonical connection on G2 mod SU3. So this SU3 bundle. And they're actually explicit singular solutions take out the origin. And I think Yangxu Wang deals with the problem on an open ball in R7, take out the origin. But here are singular explicit solutions on the whole, outside, all of outside the origin, going to infinity. But as I said, sadly, this doesn't actually work, which would be very nice if it did. There's no smooth exponentially bound. By exponentially bounded, I mean that there might be solutions that grow exponentially, but the norm of the curvature grows exponentially, but I'm not really very interested in those. So I'm putting that caveat there. G2 invariant monopoles on R7 with gauge group spin 7 or SO7. So actually, yeah, it's not just this ansatz, but if you write down what the equations would be for the general spin 7, gauge group spin 7, SO7, G2 invariant monopole on R7, you actually get that it reduces to the ODE that I wrote down. And the proof involves maximum principle. It's not particularly hard, and some other monotone quantities. And at the moment, me and Derek are trying to sort of use the insight from these monotone quantities to see if we can prove something without the assumption of symmetry. But okay, well, that was a bit disappointing. And so let's change gears. Let's look at something a bit more where we do have solutions. That might be more fun.
But there are solutions where you have less symmetry.
There are solutions where you have less symmetry. I mean, you can just take the product of something lower dimensional. But we want something that's genuinely, comes from R7 rather than something lower down. Right. Yeah, the hope would be to get a standard monopole, like there's a sort of standard instanton, but that doesn't seem to be the case. Okay, so are there any questions about this? I'm now going to switch gear and talk about something different. So last chance.
There was another question like that. So if you take the R8, and you dimensionally reduce to R7, you get a G2 manifold.
Yes.
But that's now singular.
Well, if you dimensionally reduce, you'd have to make both things. What's the answer?
I think the point is that when you dimensionally reduce, you're having to take something that has infinite action. In one
Right.
dimension.
Right.
So it's not going to be something that you would recognize from higher dimensions. From Yang-Mills to Holonomy.
Right.
I mean, the Holonomy equations are one-dimensional reduction of Yang-Mills, something with Yang-Mills, but the solutions that are finite acting R3 are infinite actually.
Right. Yeah. They would.
I was just wondering what the dimension reduced thing is anyway.
Oh, it just wouldn't have the right gauge group.
I see.
So it wouldn't be covered by this theorem. It would be, SO8. All right. Okay. So, right, if there are no more questions, I'm now going to talk about instantons on ALC manifolds. Okay, so there is going to find another ODE system to look at. And this has some sort of precedent, I guess, in what I'm doing with Lorenzo Foscolo and Callum Ross as part of a wider project, is you can use cohomogeneity 1 ODE methods to construct examples of instantons on four-dimensional, what are called ALF geometries, for example, Taub-Nutt and Atiyah-Hitchin. And the ones for, Atiyah-Hitchin seem to be not studied. People haven't studied these yet. One could try doing the same thing for the G2 analogs of these ALF geometries. For example, what's called the ALC B7 family, which was constructed by Foscolo, Haskins, and Nordstrom. And this was studied for one of the members of this family by Jason and Gonzalo Oliveira. It was called the BGG metric, which is one of this family. So there, you're getting an ODE system where the actual coefficient functions are all explicit. So in general, the B7 family is not explicit, so you don't know, you don't have as much control over the ODE system as you'd like. So it's a bit more difficult. Time. Okay. So what are ALF and ALC geometries? So I'll tell you a bit about them. They're Ricci-flat, irreducible, non-compact Riemannian manifolds. In particular, by the splitting theorem, this implies that they only have one end. And along this end, the metric converges to the following thing. It looks like the sum of a metric on a cone, Ricci-flat cone of one dimension lower, plus some, you have some S1 bundle over this Ricci-flat cone, and I have a S1 invariant one form and a connection form on this S1 bundle, and then I have some length of this S1 fiber that I can play with. Okay, in the three-dimensional case, basically this Ricci-flat cone is usually just R3, maybe minus some points. But in the G2 case, next slide. In the G2 case, the Ricci-flat cone is also Kähler on this end. So I get a Calabi-Yau cone metric with a Kähler form omega and a holomorphic volume form capital omega. Okay. So that will come into play later when we look at the solutions to my instanton problem. so the B7, what is the B7 family? It lives on S3 times R4. It's parameterized by, so in one parameter family, it's parameterized by this, this L. This L here. It's length of the circle fiber. And the Calabi-Yau cone that it fibers over is called the conifold. So the underlying complex structure is the vanishing of this, this polynomial in C4. It's the vanishing locus of this polynomial. And there's a cohomogeneity 1 symmetry of SU2 squared times U1. Right. I'm going to write down explicitly what that is, just for people who are interested. So this acts on S3 thought of as SU2 times the quaternions. And I send this to Q1 P Q2, and this is E to the I theta. Sorry. And this is Q1 bar. Okay. So and actually this S1 action is the asymptotic circle fiber, this action here, that just rotates the R4, the quaternion direction. That is the S1 action that is the circle fibration. And note in particular that this actually doesn't extend over, some of the circle fibers on the whole thing are degenerate. Like, this doesn't act on if you are at S3, so when V is 0. Okay, and the metric. So, like I said, M is S3 times R4. In our previous description, I take out this copy of S3, S3 times 0. And I have something that's diffeomorphic to the infinite interval times S3 times S3. I choose a basis of SU2, so a standard basis, but I'm doing this push-forward thing that I said before, this plus and minus, where I'm taking the diagonal, anti-diagonal embedding, E1, E2, E3, and E1, E2, E3 minus. And then I'm writing the metric is similar to the Bryan-Salomon, but now I have I have 4 functions, and one of these functions is describing what happens on the circle fiber, one of the S3s diagonally embedded, and the one S3 that's anti-diagonally embedded. Okay, and these satisfy some ODEs that come from this thing being G2 structure, like closed and co-closed. And in the case that this the asymptotic circle fiber L equals 1, this is the BGG metric, and there's an explicit solution to this ODE. Okay. Right, and my instanton ODE, I'm going to focus on gauge group SU2. And of course, there's only a trivial, topologically, there's only a trivial SU2 bundle on S3 times R4. So I choose a connection in the following way. I take the identity map between the subspace of the Lie algebra of SU2, spanned by E1 and E2, take the identity map here, and I take the identity map on the subspace spanned by E3 and E3. So that's the map into SU2, from the tangent space into SU2. And then I multiply by some functions, f and g, and some, for reasons of, it makes sort of solving the problem a bit easier, I multiply these by the metric coefficient functions A1 and A3. Okay. So the ODE I get at the end, after some massaging, is just this ODE here, where h is some function of the metric coefficients, and f and g are telling me something about my connection. They're determining the connection form. Okay, seems pretty simple. Oops. Right, so it's just a summary. This is the SU2 squared times U1 invariant, G2 instant on ODEs. Right, that's what I just said. Gauge group SU2, and H is a function of the metric. Fine, so it's an ODE. We know we like ODEs, they're usually nicely behaved. And so Jason Lotte and Gonzalo Oliveira looked at this ODE when everything was explicit. So H was some explicit function of my variable. And in that case, you can say a lot more. But even then, you still don't get everything. You still have to do a little bit more work. So I'm going to describe the qualitative picture of what happens. So this picture is essentially contained in Matt Turner's thesis, which looks at the case of the BGGG, which is parameterizing all solutions. What we've been doing is sort of trying to move away from this BGG metric. So I'll describe that now. So you look at the space of initial conditions of my ODE. Remember, this is just normal ODE. I can just take the initial values, and I get some solution for some small time. And then I want to understand what the space of initial conditions for my ODE are, which give rise to complete solutions for all time, for some fixed value of L. And at the moment, we can only do L sufficiently close to this BGGG metric with L equals 1. But we expect that this picture in some way holds for all the way, at least for L very large. Okay, so the picture is as follows. I have a line, it's a line of initial values here with f0 equal to 0, which is just abelian solutions. And this just comes from the fact that my S1, this S1 action generates a killing field, which killing fields turn out to satisfy the G2 instanton equations. So that's why I can just take any multiple of this killing field and I get a solution here. So we expect to see that. And then I have this intersects another curve. It's actually continuous. And solutions to one side of this curve exist for all time. And solutions to the left of this curve, apart from these abelian ones, they blow up either at infinite time or at some finite time. And so that's a bit mysterious. Why am I know I've explained the abelian solutions, but why are these other things happening? Why have I distinguished two different colors on the picture? So what the green and the blue are all the complete solutions. So they extend over the S3, they extend over infinity. The only thing I haven't highlighted is everything outside, which either become unbounded or blow up at finite time. The blue ones, yeah, so everything to the right-hand side of this curve extends over S3 and extends to infinity.
You have an analytic formula, do you, for this?
No.
Is it bifurcation, or is it?
What you can say is that the continuous curve comes from, well, you'll see in a minute. I'll tell you what this continuous curve is. But it's really an intersection of two different curves, like this green thing. So if you recall that this was what happens to a ALC metric, I get my metric along an end converges to a Calabi-Yau cone, product of a Calabi-Yau cone plus this maybe squashed S1 fiber. So I can write a general S1 invariant connection, sorry, I should say instanton, on the end, so as a connection on the Calabi-Yau cone plus a Lie algebra valued, a connection on the S1 fiber. So I can write that as some section of the adjoint bundle phi tensor with this S1 connection form. And then I'm going to stick a factor of L here just so that everything is unit norm. So it's a fact that if I write down the G2 instanton equations for this on this end, I actually get what's called the Calabi-Yau monopole equations. So it's another kind of generalization of this 3D monopole, which looks like this. So I take the curvature of the connection, little a, on the Calabi-Yau cone. I wedge it with the Kähler form, twice the square of the Kähler form. I say that's 0. And then I also need that the curvature wedge, the real part, the holomorphic volume form of this Calabi-Yau, is equal to the Hodge dual of the covariant derivative of the section of the adjoint bundle phi. That's the Calabi-Yau monopole equation. And what's nice is that typically, for solutions to the Calabi-Yau monopole equation, along this end, the norm of the Higgs field is constant. So this comes from the fact that the norm of the Higgs field is subharmonic, and under suitably nice conditions, this is actually, bounded, for example, this will converge. So this is sort of explaining, this Calabi-Yau monopole is explaining what's going on here. So really, what this curve is parametrizing is when my asymptotic Higgs field, the asymptotic value of my Higgs field, is converging to 1 over 2L. The exact value of this is kind of unimportant in the sense that if I look at the Calabi-Yau monopole equations, if I rescale, I can rescale my cone and then also rescale my Higgs field to change the mass, this constant that it converges to. So that's not so important. What is important is that it is there and what the relationship is with L. So yeah, this curve is parameterizing as I said, the asymptotic value of the Higgs field. So you should think of, so just to contextualize these ODE functions in terms of what I just told you, F you should think of as determining this asymptotic connection A, and G is determining the asymptotic Higgs field phi. Right, and what's happening on the interior, so here on this green line, the asymptotic connection that I'm converging to isn't trivial. I'm actually getting something non-trivial on this green line. And the curvature decays polynomially to 0. In fact, I think quadratically. And then in the interior, the thing that I decay to is actually trivial. I'm decaying to the flat connection for my Calabi-Yau monopole. And the norm is decaying exponentially to 0. Right. So another way to think about it is if I take my abelian solutions here, so there's also abelian solutions here, I can sort of fatten them up for some suitable value of the mass to get a 2-parameter family of solutions, but it stops working at some point, and that point is when I get to these non-trivial asymptotic connections. Yeah, so to answer your question, Simon, it's not explicit because it's only explicit if you look at it being parameterized by n solutions, by the, that in those parameters is explicit. It's just, the mass being this value. But you don't know what that looks like when you map the n conditions the initial conditions to the n conditions. You don't know explicitly what that map's going to look like. But you do know it's continuous. And because the ODEs depend continuously on L, the curve varies continuously. Okay. Right. So that, what I was saying, we've only been able to definitively prove when L is close to the BGG metric, which is, you'd like to know what happens in limits, but we do know very well what happens. I mean, the BGG is explicit. There's also another metric in the family of B7 metrics. Well, there's another metric appearing as a limit of the family of B7 metrics, which is explicit, which is the Bryant-Salomon metric. So there's a fact that if I take this parameter going to infinity, L, asymptotic circle length, I actually get the Bryant-Salomon metric on S3 times R4. This is a well-known thing. And in terms of the ODEs, what is that telling me? I actually get H is going to 0 as L is going to infinity. So I get the ODEs now become this. And it's not hard to see that if I set F equal to plus or minus G, that's a solution. And that's actually Andrew Clark's solution on the Bryant-Salomon metric. Right, so it is appearing in the ODEs as well as a limit. Right. So qualitatively, what's happening here is, well, this picture is a bit misleading because it's claiming that we've proved that this curve actually converges to this curve f equals g, which would be the Clark solution as L goes to infinity. Oh, oops. What we've actually proved is that the region of complete solutions, so remember that was this, this blue thing plus the green curve, does converge to, converges to a region that's bounded by this Clark solution. Remember, the Clark solution isn't a solution on B7, it's only a solution in the limit. But you do get this convergence of the region of solutions. Okay, so, I mean, that's nice that you see that something's happening here, that you're getting the solution out of a family of metrics. And let me tell you, well, we've got actually a lot of time. So let me tell you something about the proof. What? Sorry, which one? This one? So these guys extend over, what, when f equals g? What's the question, sorry? Yes, but 1 over t is a solution. Yes, but you would, like, the parameter t is, I've reparameterized things, so it's t is no longer, like, the radial direction is no longer, like, the parameter of this equation is no longer t. I mean, it's something else. Yeah, these always extend even if it's not. For B7, it's just, they're not solutions unless you have L is infinity. Right. Any other questions? No. Right. Oops, sorry. So some of the ideas of the proof. Again, a lot of the techniques are contained in Jason's paper with Gonzalo and also Matt's thesis. But for us, it's really understanding how this, what the L equals infinity, L goes to infinity behavior is. So the idea is you prove existence of, so as in Jason and Gonzalo's paper, you prove existence of sort of guess open subsets of complete and incomplete solutions. So I can just write them down. So they look kind of like this. And this is incomplete. All right. So yeah, everything here is incomplete. And then you have to prove some sort of comparison lemmas to show, and again, a lot of this is in Matt's thesis, to construct this curve for some fixed value of L. You have to, hang on, that's not very clear, is it? This curve of where you have polynomial decay, you have to show closeness of this open subset of complete solutions, which works by comparison argument. So you look at sequences that sort of go tangential to this open subset, and you show that has to be closed. So there must be some boundary that is also complete, and then you use some sort of mapping theorem to say that okay, I have mapping two closed subsets of R2 to each other. And that also requires you to know what parameterize the solutions at infinity, which is fairly involved. But here we can just sort of apply what's in Matt's thesis and get that you have this curve, some fixed value of L. The problem is, at the moment, we can't prove that you can do this. The intersection point of these open subsets is at this point. We can only prove something like this happens, where you have the same open incomplete subset, but your complete subset might not intersect it in a way that you can, so you still have this tangential business going on, but you don't know whether you can exhaust all possible solutions here by moving in this tangential direction. However, you do know what happens as L goes to infinity, so this is incomplete, is that this set moves uniformly towards this guy. This is as L goes to infinity. So you have to show, right, you can show that basically you can prove this incomplete subset is always there, and that your complete subset basically exhausts all possible solutions, so you must have this convergence. However, it doesn't tell you very much about how smooth this is, or it's a very bad convergence. So what we still needed is to, right, we know that we might be able to do this, but we need to control the behavior. So something horrible could go wrong with this curve as you move away from L equals 1. You don't know, in this picture, something very horrible could happen. Eventually it settles down to this Clark solution, but you don't know between there what do you get. You also want to understand there's a sensible rescaled limit as L goes to infinity, where you keep the size of the circle constant, this asymptotic circle fiber constant, but then you shrink down the S3. And that's describing what's happening as you're going very close. You're getting a one-parameter family of Clark solutions, but then you should also have another one-parameter family of solutions which are appearing in this rescaled limit, which is leading you to a two-parameter family of solutions for L finite, but very large. So work is still ongoing, but that is that's the end of my talk. So if there's any more questions, please ask me, and thank you very much for listening.